as everybody, right? And he has been in Utrecht in the PhD, together with Cambridge and Leiden, if I'm not mistaken. And he also has worked in the MPA, Institute for Astrophysics, right? So he's an expert on galactic stellar evolution across cosmic history. And yeah, thank you very much for coming here. And please, whenever you feel like starting, go ahead.
Sounds great. Thank you so much for your kind introduction. Thank you for the invitation for having me this week. It's been really wonderful to meet so many of you, to talk science, and I really look forward to continuing those conversations into the future. Yeah, I would like to talk about how stellar clustering, the clustering of stars at their formation and thereafter, has really shaped our origins, from the formation and evolution of galaxies like the Milky Way to the formation and evolution of planetary systems like the solar system. And to start that, I would really like to start at the largest scale. So
sorry,
yeah.
Shall I make more dark here and more light there?
This is good, so.
You prefer like
Yeah,
this?
I prefer like
okay.
We went through all light settings.
Okay.
And this was the preferred one.
Okay,
so.
okay, sorry.
So I would like to start the journey on the very largest scale. So here you see the cosmic web from illustrious TNG. Sorry, Raoul. Could have picked one of your simulations. And this is tens or hundreds of megaparsecs across. And what I would like to imagine when I look at an image like this is that in every pixel that you see here, there are countless and countless planets. And of course, there is an enormous difference here in the range and scales, right? There are many planets in every pixel, and across this image, it means there are even more. But if you want to sort of connect these two scales, going from the structure, the initial structure of the universe, the cosmic web, down to the eventual emergence of planetary systems, there's of course an enormous gap to try and understand. And if you want to bridge this gap, you're looking at a stunning 18 orders of magnitude in spatial scale. It's very intimidating to try and cross that gap. So what you typically do is you try and cut that up. That's the only way of addressing this question. If our existence is one of the biggest multi-scale astrophysics problems. And if we want to understand that, how we exist in this universe, how we get there, we need to cut this up into smaller pieces. So what we do is we go from the large-scale structure in the cosmic web, we go down to individual galaxies. Within those galaxies, we then try to understand how individual stars and stellar clusters form. Like here, there's another 3 orders of magnitude in spatial scale. And then you can ask, okay, within those young stellar groups, there must be planets forming. And indeed, they form here in protoplanetary disks around the stars. There's another 4 orders of magnitude down in spatial scale. And I typically think at this point, we're nearly there, because I come from these scales. I think, okay, by the time you're at a protoplanetary disk, that's it, right? No, not at all. 7 orders of magnitude in spatial scale. You need to go down further to get to a planet like Earth. So this is the challenge at hand, to try and bridge these scales. Now, what you see here is I kind of have put stellar clusters in the middle. And there is a reason for that. Stellar clusters are at the center of this web of connected scales. Towards the large scales, stellar clustering drives the Baryon cycle within galaxies. It drives how the gas is converted into stars, is blown out again, is all related to stellar clustering. And that's what I'll talk about in the first part of this talk. But then secondly, you can actually use the oldest stellar clusters in the universe to try and trace galaxy formation and assembly, to understand how we get from here to there. Then from that, if you zoom into smaller scales, within these stellar clusters, it turns out that the clustering of stars perturbs and destroys protoplanetary disks, and therefore it affects the planet formation process. And then finally, it turns out that the eventual properties of the planet population are modified by such external effects. So this is basically the overview of what I'd like to talk about. And I'll start at the beginning. I'll start at how stellar clustering drives the Baryon cycle within galaxies. And the key point here is that the clustering of star formation and feedback, so the impact of the radiation and the energy and momentum output of the stars on the surrounding interstellar medium, determines what the properties are of the galaxies that eventually come out. And I think a really nice example of this is given by the work I did earlier this year with Ben Keller, who's working with us in Heidelberg, is you see here 4 galaxy simulations that have exactly the same initial conditions, exactly the same physics. And what Ben did here is he changed the delay time after which supernovae start going off within the star particles. So star particles being born, here a supernova goes off immediately, here it takes 30 megayears. So you see here immediately that if you change that delay time, you actually get very different galaxies. And the reason for that, you can understand if you look at here at the 2-point correlation function of the young stars. So it turns out if you go to the longer timescales here, it turns out that the stars end up being more clustered. And because they're more clustered, the supernovae are going off close together and they're able to blow bigger holes within the galaxy. So it's a very, very sort of simple, basic physical process, and you see it has a radical impact of what the galaxy looks like. And the problem with this is that many of the choices here make sense, and we don't know which of these capture the correct physics. And this is only talking about supernovae, but the problem of feedback is much, much bigger. Feedback is a combination of all kinds of different processes. Melanie talked about those on Wednesday already. So stellar winds, supernovae, photoionization, radiation pressure, all of those are happening at the same time. We don't know how these interact non-linearly, and we don't know how their impact on the surrounding medium is affected by the fact that they're all happening at the same time. So the way that we've been kind of trying to overcome this problem is by using the observational constraints that Melanie talked about on Wednesday to formulate new models for stellar feedback in galaxy simulations. And the basic idea is that if you look at the observations, you can constrain the timescales on which the feedback is happening by looking at the correlation between the gas that the stars form from and the young stars themselves. If they're sitting in the same place, then it takes a long time for the stars to blow up the gas. If they're not sitting in the same place, then the stars blow up the gas very quickly. So using that type of constraint, and that's now possible using ALMA, Melanie has basically, with her team, been constraining these sort of evolutionary timelines where you go from molecular clouds here in orange to the emergence of massive young stars here in purple, or whatever the color is. And then the duration here tells you how long it takes those young stars to get rid of the gas. And we can then use those timescales to determine exactly what the input momentum is that you get from stellar feedback and put that into galaxy simulations. If you want to know more about the details, of course, I'm skipping over here now, but Melanie gave a great talk about this on Wednesday and it's on YouTube. So if you were not here on Wednesday, you can look at it. But the key point here is that what these observational constraints show is that molecular clouds only live for 10 to 30 million years. That's about 1 dynamical times. The clouds really have time to gravitationally collapse, and that is it. Then the cloud is gone. And the reason that the cloud is gone is that it's dispersed here in only 1 to 5 million years by stellar feedback. And these timescales are so short that it's by feedback that happens before the first supernova explosions. So the example that I just showed of how it matters how long you wait for the first supernovae, well, that's actually exacerbated in a way by the fact that you need to account for this pre-supernova feedback that happens already before the first supernova goes off. And that is what we can now do here. So we can use those timescales to calculate what the terminal momentum is from the feedback. So you have a stellar population, and how much momentum does it impart on the surrounding medium, on the cloud, by the end of this feedback phase? And that's given by this relatively simple expression, where epsilon SF here is the star formation efficiency. So it's the fraction of the cloud that's converted into stars. And we can now measure that, as Melanie talked about. Then that happens on a timescale here. That's the feedback timescale. That's the duration that you see here. So that's also an observable. And then the final one here is the cloud radius, which we can also observe in observations. So all of those quantities are observables. And this here is a sort of a fudge factor that varies by a factor of 2. It can take values between 0.5 and 1. And it turns out, as I'll show later, is that the value of this number actually does not impact any of the results. So the results are insensitive to that. So what that means is we can just purely observationally determine what the momentum input is due to early stellar feedback. And this is, by the way, is not the total momentum input, it's the specific momentum input. So it's the momentum per unit stellar mass that you form. So this is very straightforward to implement in simulations. When you form stars, this will tell you how much momentum those stars produce at the end. So what you can then do is you can assume that the expansion of the shell is self-similar, so it follows a power law relation. And then you basically get this other form, which is now in a time-dependent way, is the total momentum that has been imparted. So you can take the time derivative of this, and that gives you then for every time step exactly how much momentum you put into the surrounding medium. Now, what does this look like, the specific terminal momentum? Here it's shown as a function of galactocentric radius for the observed nearby galaxies. It is remarkably constant. It doesn't actually show that much scatter. Here it has a certain value, okay, there's a certain number. The scatter is actually of the order a factor of 2. And that's extremely narrow given the wide variety of sort of environmental conditions that we're probing in the nearby universe. So what to first order we've been doing is basically use this number as that terminal specific terminal momentum that you put in, and then put that into simulations. And that is what now has motivated the new suite of simulations called EMP, for empirically motivated physics, or electromagnetic pulse, whatever you prefer. And the idea here is that we solve the hydrodynamics equations on a moving mesh using Volcker-Springel's Arepo code. We use explicit cooling of the interstellar medium down to just a few tens of kelvins. We track the chemical abundances of 36 chemical elements and their isotopes. We track 100 chemical species, basically, so that we also can do galactic archaeology afterwards, which actually figure out how the baryonic physics change the chemistry of galaxies. We have, as a result of this model, realistic phases of the interstellar medium. We have a new star formation model that accounts for the dynamical state of the clouds. So whether they're collapsing or expanding, these types of things go in and determine how quickly the clouds form stars. And then this empirical feedback model that I just showed, basically using the observations to put in exactly what the stars are doing to the surrounding medium. And in addition to that, we also model the individual supernovae that are going off, because that you can kind of predict. In addition, we have a subgrid model for star cluster formation and evolution that I will discuss in the second part of this talk. And all of that gives us the opportunity to follow the baryon cycle from the initial collapse of molecular clouds down to the emergence of stellar populations and the evolution of those stellar populations then over the course of cosmic history. And this is really, as you can see, is really a team effort. So I'm basically showing everybody here who's involved in this major effort, and all of these ingredients are basically due to their amazing work on this. So this is what empirically motivated feedback looks like. This is an isolated galaxy simulation, and you can see basically how the gas here, the interstellar medium, is rotating, is being structured. You see small explosions happening. This is the pre-supernova feedback, that every time stars form, start sweeping up the material. And the interesting thing we can do here is, of course, we can switch on and off the empirical feedback. And this is what that looks like. So here on the left, you see the same simulation for only supernovae. Here on the right, you see the simulation in this case for a certain number of that alpha parameter. But you see again, is there are already differences between both simulations. And it turns out physically, we can understand what is happening. So this shows the probability distribution function of the gas density at the time of the first supernova explosion in a particle. So all of those particles or star particles are being formed. It takes some time for the first supernova to go off. And that supernova will go off in a certain environment. There will be gas of a certain density. It turns out that if you only run supernovae and don't have this empirically motivated early feedback, the typical density in which the supernovae go off is higher than if you do include the empirical feedback. And as you can see for both alpha parameters here, there's not really a difference. Now, it turns out that that difference arises because without the early feedback, if you only have supernovae, the clouds can collapse much further before feedback starts stopping the collapse. So the densities end up being higher. And because the densities end up being higher, as you see here, you visually, if you look at the stellar distribution, you see a radical difference. You've got a lot more stellar clustering if you only have supernovae, if you wait long for the feedback to start doing something. And it's because everything just collapses. You get radical clustering here. Whereas if you include the early feedback from the observations, you get a much smoother and much more gentle sort of stellar disk. And you see that directly here again in the 2-point correlation function of the stars. Again, this is just for supernovae only, and this is when including the empirically motivated early feedback.
Diederik, sorry to interrupt. So this is the clustering of, your stellar particles,
yes.
Right?
Yeah.
So I'm just trying to think. So of course they represent like a stellar population.
Yes.
So how much would it change of course, with resolution, because if it's much smoother and you have much.
Yep. For those online who might not be able to hear the question is, okay, how much does this depend on resolution? Because of course, this is the clustering of the star particles in the simulation, which is set by the resolution to some extent. So we've done a convergence test, and it turns out for particle masses between 10 to the 4 and 10 to the 5 solar masses, the results are indistinguishable. When you go to higher resolutions, you actually start violating one of the key assumptions of the model, which is that you can model giant molecular cloud destruction from the observations as coming from a central source. If you start to go to something like 10 to the 3 solar mass resolution, you start resolving those different stellar populations that form within the cloud. And if you then put in this terminal momentum that I showed, for every source, you get momentum cancellation because there's no longer one central source. No, you now say you get 2, and they start pushing against one another. So then the momentum you put in cancels, and you no longer get out the net momentum that you actually put in. So this model is designed to operate at a certain range of resolutions, and within that range, it's really well converged. So this is just the internal structure, right? So the internal stellar clustering of the galaxy changes. But it turns out, actually, this has major implications for the global baryon cycle within the galaxy. So what you see here is the outflow mass loading. So it's the outflow rate in units of the star formation rate. So basically, if you form a solar mass per year in stars and you have an outflow of 1 solar mass per year, then you're sitting at 1. And what you can see here is that, again, after the initial disk settles here towards the end, there is an order of magnitude difference here between the supernova only case and the empirical feedback case. And again, that is because the supernovae only simulations have very clustered star particles. So these blow much bigger holes and blow larger outflows. Whereas if you include the early feedback, the star formation is a lot more dispersed. You get gentler outflows that are actually not escaping the galaxy. They just redistribute the interstellar medium within the galaxy, keep it sort of tepid to make sure it forms less stars, but it is not blown out actually. So this is a macroscopic prediction that we can just test in galaxy surveys right now. So that is basically how the baryon cycle in this galaxy here is being driven. And this is, as I just showed, entirely dependent on the degree of stellar clustering within this galaxy. So now that we described that, now that we have an idea of how stellar clustering within galaxies works, we can look at, okay, how do the relics of that process that might have survived over the course of cosmic history tell us something about early galaxy formation in the early universe? And when I say that, I'm talking about globular clusters. So globular clusters, many of you will know, are typically old structures of the order 10 gigayears, almost as old as the universe itself. They're massive, housed of the order 10 to the 5 solar masses of stars, and they're compact. This image here is only 10 parsecs across. It's tiny. And the key questions that people typically ask when they're looking at globular clusters are twofold. One is, how did globular clusters form? Where do they come from? And what do they tell us about the formation of the Milky Way, those earliest phases that the Milky Way formed that we can no longer see today? And the simulations that we've been trying to address these questions with, we've run as part of the eMosaics project. So the eMosaics project here is basically what we did is we coupled subgrid models for the formation and evolution of stellar clusters, mosaics, to the galaxy formation and evolution model from the Eagle simulation. So here in the background, you see the 25 megaparsec volume from Eagle, and then we selected 25 Milky Way mass halos initially, and we then re-simulated with this sort of combined star cluster and galaxy evolution model. And this is really the first time that we are able to completely follow the formation and evolution of the entire star cluster population across cosmic history. So it gives us a unique chance to actually try and answer these questions, like where the globular clusters come from and how are their properties correlated to the early galaxy assembly that we see, that the Milky Way experienced. So this is a movie I showed on the first slide. What you see here is a cosmological zoom-in simulation of a Milky Way mass halo. You see the initial collapse here of the initial halos and the gas within them. You see bubbles being blown here by the feedback. And then you see colored dots appearing. And these colored dots are the star clusters within the model. And they're color-coded here by their metallicity, by their chemical composition. So you start kind of bluish, and then as you get more metal-rich due to chemical enrichment, you go towards this sort of yellowish color. Now, here the central galaxy is forming with its own population of stellar clusters orbiting. What you see here is another galaxy coming in. And what you notice immediately is that the clusters of this other galaxy are bluer than the ones here in the central galaxy. So what that means is they're more metal poor. And that means that basically by looking at clusters today, you might already be able to say something about, okay, these clusters came from a galaxy like this, like a smaller galaxy that came in later. And these other clusters, they may be formed in the central galaxy. Right, so that's the type of observable that you can use. So yeah, just to very briefly summarize. Again, we use the Eagle galaxy formation model here. So we get the hydrodynamics from Eagle, we get the gravitational dynamics, and we get the stellar evolution from Eagle. And then we couple that to the Mosaic star cluster model, which has a model for the star cluster formation. So what fraction of the star formation occurs in stellar clusters? What is the initial mass spectrum of those stellar clusters? These are typical formation-related questions that you ask. And these are dependent on the environmental quantities. So these are dependent on the hydrodynamical state of the gas and the dynamical state of the gas. And then in addition, we model the star cluster evolution, basically how much mass do they lose per unit time? And that is dependent on the stellar evolution, because stars lose mass. That means the clusters lose mass. But it's also dependent on the gravitational dynamics. It's dependent on the tidal field. Basically measure the tidal field at every time step, and then apply the corresponding dynamical mass loss to the clusters. And that way we're able to basically predict what are the initial demographics of the clusters being born at every moment in time, and then how do these get disrupted over the course of cosmic history. Sylvia.
Sorry to interrupt. So here in this, what do you do? So you take some of the stars that are coming naturally within the hydrodynamics of Eagle and you cluster them together, or you add them as a sync particle?
So basically every star particle has that it's born in the simulation has its subgrid cluster population. Okay. And there is a certain fraction of the particle that we assign to that cluster population, and that's based on this fraction of star formation that occurs in clusters that we can calculate depending on the local environmental conditions. And we sample from the initial star cluster mass function. And then when the clusters lose mass dynamically, when they lose stars, it basically goes within the same star particle, goes into the field star budget that we're keeping track of within that particle. So the model is entirely subgrid, and that is basically how we can track it across the simulation. It's numerically totally impossible to do this for the volume that we're covering with any sort of more explicit method. So as I mentioned, we had 25 initial zoom-in simulations of Milky Way mass galaxies and their satellites. These were not all. We've run hundreds of simulations to really understand how important the different physical ingredients are, to convince ourselves that sort of the fiducial model that we're running with is stable, which elements we can trust. And then recently we've completed a 34 megaparsec volume, you see here. It now includes of the order 100 Milky Ways and goes up to almost a Fornax galaxy cluster mass system here. So we really start spanning the entire range of galaxy masses now. Now there are two main results that have come out of eMosaics. One is that we can explain these old globular clusters and their properties with exactly the same model that we can use to reproduce the young cluster population that we see forming today. So globular clusters are not weird beasts that could only form in the early universe. No, we can apply exactly the same physics just to the conditions that were prevalent at high redshift. So higher gas densities, more frequent galaxy mergers, these types of things. That allows us to produce these sort of extreme stellar clusters that we now today see as globular clusters. The second result is that yes, we do find that the properties of those globular clusters are actually correlated with the galaxy formation and assembly history. And that is what I'd like to focus on. So historically, the globular cluster age metallicity distribution has been identified as a very important probe of galaxy assembly. So here you see, this is the globular cluster population of the Milky Way, here shown as a function of age versus metallicity, so chemical composition. And what you see here is this very sort of, unique feature that catches the eye, where you see this bifurcation. So you get this branch of clusters that basically goes straight up. So they're all old, and actually it's cut off here, but if it were to continue, it does bend over here a little bit. So if you look at this branch, it chemically enriches very quickly, and at a given age is more metal rich than this other branch. So this other branch typically at a given age has a lower metallicity. And that is why people think, because lower metallicities usually correspond to lower mass galaxies that don't enrich their interstellar medium as quickly, that these clusters came from lower mass galaxies that were accreted onto the central galaxy later. So this, for that reason, is called the satellite branch, typically, and this is called the main branch or the in situ branch. Now in e-mosaics, we can make this type of diagram. So here I'm now showing for 6 Milky Way mass analogs, I'm showing this age metallicity distribution, where in colors, you again see the globular clusters. They're color-coded by the galactocentric radius. So more central is more yellow. And the contours show the field star formation history. So basically, just where any of the stars in the galaxy form. So at which metallicity and at which age. And what you see is that whenever there are intense episodes of field star formation, like when the contours are close together, the galaxies also form globular clusters. So globular clusters are byproducts of the most intense episodes of star formation in these galaxies. Now, all of those diagrams sort of do the same thing in that they start metal poor long ago, and they become more metal rich more recently. That's what we expect from cosmic evolution. But there are qualitative differences. Some of those are super steep, like this one here, and others are very shallow, like that one there. And it turns out that that is entirely related to the assembly history. So here I'm now showing the merger trees of these galaxies. And it turns out the really steep ones have rich merger trees, basically rapid galaxy assembly, where all of the material came in very quickly. Whereas the shallow one here has a very sparse merger tree, where the galaxy formed a lot less rapidly. And that means that we can basically use these types of diagnostics to infer what the properties of these merger trees are. Now, another point I'd briefly like to make is we can hear also, like here you see something like what in the Milky Way we call a satellite branch. And indeed, we can track in the simulation, these clusters indeed came from satellite galaxies and were accreted later on. So we can now basically start linking individual globular clusters to the galaxies that they came from. Now, this was just age metallicity space. With the Gaia satellite, we now have also the ability to constrain the orbits of the globular clusters in the Milky Way. And those orbits also tell us something about where these clusters came from. And this is showing basically the orbital structure of globular clusters in the Milky Way here in energy angular momentum space, where blue is basically just the in situ population that formed within the Milky Way. And then the other clusters here by Massari and collaborators were basically clustered in kinematic space, in orbital space. And basically what they did is they selected groups of globular clusters that had similar orbital characteristics and said, okay, because these are moving in the same way, they probably came from the same galaxy. So that way they identified 5 groups of globular clusters that they believe came from 5 different galaxies. Now what we can then do with the simulations is say, okay, let's take those 5 groups and try and infer what the properties were of those galaxies that they came from. And we did that by using e-mosaics, by basically taking the globular cluster ages, metallicities, and orbits from e-mosaics, and then training an artificial neural network on the simulations to link these properties to the mass of the galaxy that the clusters came from and the redshift at which that galaxy accreted onto the central galaxy. We trained that on over 200 accretion events on Milky Way mass galaxies that we have in e-mosaics to then basically predict what these properties are. And this is the result. So we have these 5 accretion events, 5 groups of globular clusters that were identified by Massari and collaborators. And this is showing the posterior probability distribution of the mass of the host galaxy that these clusters came from. And what you see is in each panel, there is, except for that one, there is more than one histogram. And the reason there is more than one histogram is for some clusters, their association is a bit ambiguous. We don't know if it came from this galaxy or maybe from this other galaxy. So we looked at basically all different permutations to see, okay, does it matter like exactly how we do the detailed membership or does it kind of work well? And it turns out, as you see here, most of the histograms are very similar. So, okay, what we see here is basically that 3 of the galaxies had relatively similar high masses, between 2 and 3 times 10 to the 8 solar masses. And then the 2 other ones had a mass of maybe 10 to the 8 or a little bit less solar masses. And these are, several of those are well known. This one here is Sagittarius. It's a well-known merger that is still, we see the sort of the final bit of that still happening in the Milky Way. Gaia Enceladus was discovered using Gaia. Kraken here is a new galaxy. We actually predicted using e-mosaics, and now we found the debris. Then we have here Sequoia and the progenitor of the Helmi series. Now, despite the fact that these masses were very similar, it turns out those galaxies accreted at very different accretion redshifts. And that is basically, you can see that observationally, because the Kraken globular clusters are much closer to the galactic center, and that means they accreted a lot more early. So we have an accretion redshift here of 2.2, 2.3, whereas Gaia Enceladus then accreted at 1.4, and Sagittarius, as I said, is still sort of ongoing. So these galaxies had similar masses, but they accreted at very different times. And because the Milky Way was growing during that time, the mass ratios for those galaxies were very different. So at the time that Kraken merged with the Milky Way was still a really small galaxy. Now that Sagittarius is merging, the Milky Way is a big galaxy. So it means that the merger ratios are very different. And it means that Kraken was actually the most major merger that the Milky Way ever experienced. I say most major, it's not major at all. The stellar mass ratio here is 1 to 30. So the Milky Way never experienced a major merger. And that might be why we exist. And I'll get to that. So putting these results together, here you see the merger tree of the Milky Way that we've basically reconstructed using these 5 galaxies here. So based on the statistics of the globular cluster population, we expect 15 mergers. So we've now found 5. You see here in the center, you see the mass of the Milky Way growing. It's color-coded here by the stellar mass. It's a function of redshift. And here you see different accretion moments of those different galaxies. Now, I think this is really exciting because we used to be able to draw merger trees for simulations. And the fact that we can now start doing this for real galaxies is a little bit surreal to me still. But it's really because of the simultaneous arrival of Gaia and then the development of these simulations that we can start to do this. What is also nice, I already mentioned, is that the existence of Kraken was a prediction from e-mosaics. We predicted that based on the existence of some really metal-poor globular clusters that were quite young. And it's not only been found in the globular clusters now also in the field stars, people have now found the debris of Kraken. So that gives us some confidence that we can actually really use the simulations to learn something concrete about the assembly of the Milky Way. So this is for the Milky Way. We're going further. As I mentioned, we have this 34 megaparsec volume here, shown in gas, dark matter, metals, and stars. And with this volume, we can start to do this type of science across the galaxy population. And this is work by Sebastian Trujillo Gomez, who is working with us in Heidelberg on this. And what he's been doing is been looking at the galaxies in this large volume, and basically looking at the globular clusters in those galaxies, whether they formed within the galaxy or ex situ, whether they were accreted from another galaxy. And he's been using artificial neural networks and random forests, so basically machine learning, to predict based on observables, quantities that you can observe in those other galaxies, to predict whether indeed these clusters formed within the central galaxy or were accreted. And he can now, after taking out sort of the ambiguous cases where it's not really clear, if he looks at the cases where he can do this, he gets an accuracy of about 90%. So this is now really possible to look at individual globular clusters and say, did this cluster form in this galaxy or did it form in another one? And then finally, with this volume, we can do sort of all sky globular cluster science. So this is showing the 2-point correlation function of the gas, the dark matter on cosmic scales. Here the stars in black, and the gray here is now showing the same thing for globular clusters for the first time. And what you see is that the prediction is on sort of intermediate scales between 20 kiloparsecs and 700 kiloparsecs, that the globular clusters show more clustering than the stars, whereas on smaller scales, the stars win. But overall, of course, this is a second order effect. Overall, the globular clusters are predicted to largely just follow the distribution of stars in the universe. So this is a prediction that we will be able to test with Euclid going forward. Okay, so stellar clustering drives the Baryon cycle within galaxies, and the relics of that process we can use to trace galaxy formation and assembly. We can learn how galaxies like our own Milky Way formed. But what is now the impact of the stellar clustering as we go down to smaller scales? How does stellar clustering perturb and destroy protoplanetary disks? And the reason that we expect this to happen is that star formation is hierarchically structured. this is a simulation of a star-forming cloud. It could have been a simulation of galaxy formation. It actually looks very similar. It's because in both cases, it's just gravity that's acting. So what you see is that you see smaller structures collapsing first, and then globally they start collapsing together. And because of this substructured nature, the interactions between stars in the bound region, the dynamical interactions, but also the external photoevaporation from nearby massive stars are really common processes. And all of those stars that you see forming here are subjected to these external influences in one way or another. And we've known this for more than 25 years. So this is showing a Hubble Space Telescope image of the Orion Nebula. And here the zoom-ins show the protoplanetary disks within Orion. Now, Orion is relatively active, is the most active star-forming region in the stellar neighborhood. You've got massive stars here in the trapezium cluster. And more than 25 years ago, Bob Odell found that the protoplanetary disks here are very deformed. And they're deformed because of the external photoevaporation from the massive stars. You see these beautiful photoevaporation fronts here. And indeed, if you then look, where's the most nearby massive star, it turns out it's somewhere here. So it's exactly shaped, sort of pointing in the direction that you expect for external photoevaporation. Now, of the order 10 years ago, I got interested in this topic myself. So this is work I did together with Maria Dojana-Ovelar. And basically what we looked at is how do the sizes of protoplanetary disks change as the local stellar density, as a function of the local stellar density. And what you basically expect is that at low densities, you don't expect any dependence at all, but at high densities, maybe the protoplanetary disks are smaller. And that is exactly what we observed. So you see basically here the disk radius distribution as a function of the local stellar number density. And it turns out that the very highest densities, and here is basically showing the statistical significance of the differences between the distributions as a function of the density, there is a deficit of the most extended disks here at the very highest densities. And this at the time was a tentative result, right? So it was, the significance was only, say, a few times 10 to the -2. But it was suggestive. And in the years since, especially with ALMA, it's now become clear that this was actually real. This was a real result. So this is now showing a more recent result looking at disk dust masses. So it doesn't really matter if you look at gas or dust in this case, if you assume a constant ratio. This is showing the dust masses of protoplanetary disks in the Orion complex as a function of the separation from a nearby massive star. And what you see here is that basically there are no massive disks in the direct vicinity of that massive star. All the massive disks are far away. And that's because of the photoevaporative effect from that massive star. It basically is evaporating the disks that are close by. Yep.
So what units has the x-axis?
The x-axis, oh, sorry, that is parsecs. This is the thing, is I overplot here a label to make it more legible, and then I forget the unit. So yeah, thank you, I'll fix that. Okay, so that's photoevaporation. That's challenging to model. Here I'm showing an example of how we've been modeling dynamical interactions. So this is an n-body simulation of a stellar cluster where we've put hydrodynamical protoplanetary disk around the stars, and you see how the interactions between the stars are actually disrupting the protoplanetary disks. So these types of processes you should keep in mind. Okay, so the question is now, okay, great, all of those external perturbations. How can we say something about how common these are? And to answer that question, we need to look at the initial density distribution of the stars. And it turns out we can derive that from the initial gas density. And so the clustering of the star formation really depends on the local gas density. And thankfully, the local gas density is really well characterized. So there was a huge literature basically showing that the gas density PDF is a log normal, and that the width of that log normal, so basically the contrast you get between the density extremes, is set by the gas pressure. So if you have higher pressure, you get larger density contrasts within your interstellar medium. So this is showing the gas. What we can then do is we say, okay, here at low densities, the gas has a long free fall time. It takes a very long time to collapse under its own gravity. Whereas at high densities, it has a very short free fall time. So what that means is that at the low densities, we're going to get a low star formation efficiency. It's taking long to collapse, so only a small fraction of the gas can be converted into stars. Whereas at the high densities, because you have a short free fall time, everything collapses quickly and a large fraction of the stars gets converted into stars. So you can basically translate this density PDF of the gas into a density PDF of the stars. And then what you get is here at this low density end, you get sort of very dispersed stellar associations that are very sparse. And at the high density end here, you get dense, compact stellar clusters. And of course, it's a continuum, right? I'm just showing the extremes here. But this way you can characterize what the initial density distribution is of young stars at birth. Now that is important because it turns out that this gas density PDF that you start with is entirely set by macroscopic properties if you assume, and that is a reasonable assumption, that star formation proceeds in a galactic disk that is in hydrostatic equilibrium. If you make that assumption, then the density PDF is entirely defined by the global gas surface density of your galactic disk, its angular velocity, so how fast it rotates, and its Tumor-Q stability parameter, so the balance between gravitational instability and shear. These are macroscopic properties that you can just define for a galaxy. And that means if you define those for a galaxy, you know what the density PDF is, and you know what the stellar density PDF is at birth. But if you know the stellar density PDF, you can predict the initial cluster mass distribution. You can sample the stellar initial mass function. You can calculate the local far UV radiation field that's evaporating those protoplanetary disks. So you can calculate the external disk photoevaporation rate. And because you have the stellar density, you can calculate the dynamical destruction rate of the disks due to stellar flybys. So we can now basically predict what the disk lifetimes are as a function of the large-scale galactic environment. And that is what we've done here. So in this figure, basically in the grayscale shows a 2D PDF of where stars are born. Here as a function of the initial stellar number density and the far UV flux density, which, these two are obviously, they're correlated. You put more stars together, you also get more intense radiation. So you see here in gray is where we predict stars to be forming. And then in the colors, you see some sequences for some observed star forming regions. You see these actually match quite well where we predict just macroscopically, where we predict the stars to form. Here, the left panel is showing this for the solar neighborhood. The right panel is showing this for the central few hundred parsecs within the Milky Way. And I'll highlight in a moment why that's important, that difference. In blue, you see here now sort of tracks or isochrones of protoplanetary disk lifetimes. So at this location, disks live for about a megayear. At this location, they live for 3 megayears. The horizontal part here is set by photoevaporation. So you go up here on the UV density axis, you live shorter because of external photoevaporation. The vertical part here is set by dynamics. So you move to the right and stellar flybys are going to destroy you more quickly because they happen more often. Now, what you see here is that typically you end up in the photoevaporation regime well before you end up in the dynamics regime. So disk lifetimes are mostly truncated by external photoevaporation. Now, in the solar neighborhood, it's only a few percent that's disrupted in less than a megayear. So it's not that much. In the central few hundred parsecs of the Milky Way, it's more than 90% of the disks that are disrupted in less than a megayear. That difference is important because we live in a very boring part of the universe. Again, that's probably why we exist. If you look at cosmic star formation, like across cosmic history, these are the normal conditions under which star formation proceeded. Star formation history of the universe peaked about 8 to 10 billion years ago. These were the typical gas densities, stellar densities, radiation fields in which stars and planetary systems formed. So this is the standard, not what we're seeing in the solar neighborhood. And that is important because it turns out that the protoplanetary disks live 5 times shorter in the central molecular zone of the Milky Way than in the solar neighborhood. Right? So we're looking at a difference of a median of 0.5 megayears to 3 megayears. Now, this is a prediction at this point, and with the arrival of James Webb, we have some approved time already for cycle 1. We can actually start testing this prediction. At the moment, it is a prediction. We can't do more. But we'll find out soon, hopefully. So now in the very final part, I'd like to talk about, okay, let's say there are environmental effects that affect planet formation. Can we see evidence that actually also the demographics, the architectures of planetary systems are modified over longer timescales? If we look at planetary systems, is there an impact of the ambient environment? So how do we do that? The problem is that most planetary systems have ages of more than 1 billion years. And at that point, the sort of the overdensity in which they were born has long been erased dynamically. So there is no way of relating, the current density that you see around planetary systems to the density that they had at birth, except if they're sitting in a globular cluster. But maybe we don't expect that many planets in a globular cluster based on what we just saw, right? So there is another way of doing this, and that is that, it's possible that even if stuff, if stars form together and they're no longer really associated, maybe they're still moving in the same way. So maybe we can find moving groups of stars that are moving in the same direction, and maybe that tells us something about what they experienced over their lifetimes. So with Gaia, again, that is now possible. So basically, to test this idea, what we've done is we've taken all known exoplanet host stars that have radial velocity so that we could quantify the 6D position velocity phase space structure. So 3 position components, 3 velocity components. And then determine the 6-dimensional phase space density around those stars, which is basically how close are they in positional space and how close are they in terms of moving together. Then it turns out if you do this type of analysis, you need to be extremely careful. Gaia has a selection function where there are complicated completeness limits, and also planetary surveys have complicated completeness limits and selection functions. So you need to be checking for biases all the time if you want to say, okay, is there a correlation between planetary properties and environment? So we've been checking for biases, and we compared the planet properties that we found as a function of this ambient phase space density and kept checking for biases, and I'll come back to that in a moment. So here I'm showing 2 examples of basically what you can expect. So this is a star, HD something, with a planetary system around it, and it's here shown in physical space, so X in parsecs and Y in parsecs, with the ambient stars. And here you see another star, WASP-12, and it's also sitting in its own sort of local stellar environment. And what you see here immediately is that in physical space, there is no substructure. Both of these are just sort of sitting in the field. And yeah, after a few gigayears, that's what you expect. But now we can look at this in kinematic space. And this is what it looks like. So in kinematic space, now showing the radial velocity within the galaxy versus the azimuthal velocity within the galaxy, you see actually that there is clustering. And HD something is sitting out here on the side. So this one is not sitting in a co-moving group, whereas WASP-12 is sitting right in the middle of a co-moving group. Right? So that tells us something that tells us, okay, these are part of sort of really different dynamical entities. And if we then characterize the phase space density around these 2 systems, this is what they look like. And we find that basically in general, the phase space density distributions are double log normals. So we have this sort of field component, and then we have what we call an overdensity component. And what we see is that indeed HD something is here sitting in the field component. So this vertical line here is the phase space density of that planetary system. And WASP-12 here is sitting very firmly in the overdensity component. So we refer to those as field and overdensity. And we can quantify using Gaussian mixture modeling what the probability is that those planetary systems belong to each of these 2 components, to either of these 2 components, right? So here the probability of being in the high component is extremely low, and here it's quite high. Now, before I continue, I'd like to make one point really, really clear, because I think this is important. This is the phase space density today. We do not know if this actually corresponds to having a dense birth environment, or if this phase space density was somehow generated later. We don't know if this reflects the birth conditions. All we know is that WASP-12 is currently sitting in a phase space overdensity. Okay, so before I actually show the results, we need to check biases. We need to check covariance. So this is now showing for sort of the field and overdensity planetary population. So we now have taken the entire planet sample, divided into field systems and into overdensity systems. We've made stellar mass and age cuts to look at as similar planetary systems as possible. And after making those age cuts and mass cuts, what we see is that the stellar mass, the host stellar mass, the stellar metallicity, and the stellar age distributions of the field and overdensity systems are statistically indistinguishable. So any differences between both populations that we're going to find are not going to be due to stellar mass, metallicity, or age differences. Basically the same distributions. We see a difference in distance distribution. And that is important because that could imply detection biases, right? If things are further away, you might be detecting different planets. Now, it turns out if we actually cut the sample at 300 parsecs, turns out these 2 distributions are entirely indistinguishable again. And the results that I'm about to show don't change if we make that additional cut. So that means that whatever distance difference exists here does not affect the results I'm about to show. And because we prefer a bigger sample, we just keep it this way. Okay, so the first result that we found is this. I'm showing here the planetary mass versus the semi-major axis. So how far it's orbiting from the host star. Here on the left, showing the distribution of field planets, so planetary systems sitting in low phase space densities. And this is showing the distribution of overdensity systems. And the immediate result here is that the median semi-major axis, so the distance from the host star, is an order of magnitude smaller in phase space overdensities than in the field. So these planetary systems are much more compact. Then in addition, there is this box here that indicates hot Jupiters. These are Jupiter-like planets, gas giants that are orbiting extremely closely to the host star. What we find is that 92% of all known hot Jupiters reside in overdensities. So hot Jupiters, these really extreme planets, that were among the very first planets, very first exoplanets to be discovered, actually, because they're massive and they're close to the host star. It makes them easy to find. It turns out that these exist because of some environmental process. We didn't really know, but now we do. And we need to try and understand that. But this is a very clear and distinct result. Other results are that it turns out stellar clustering affects planetary multiplicity. So there is a known result from the Kepler mission that there is an observed excess of single planet systems. So if you basically model what you expect your multiplicity distribution to be like, the number of planets per system, you can basically predict what that should be. But then in Kepler, there is this enormous excess of systems that only has one planet. And this is called the Kepler Dichotomy. Basically, you need two distribution functions to model that global distribution. What we find now is that this excess is largely due to the planets in overdensities. So the planets in overdensities, the planetary systems in overdensities, very frequently only have one planet, whereas those in the field have a much flatter distribution here. So that suggests, again, that somehow the phase space overdensities have been perturbing the planetary systems, maybe reshuffling them one way or another, such that in the end, only one planet was left. Another result here, which is a paper by Melanie, is that stellar clustering affects the correlation between planet radii within planetary systems. So this is, again, a great result from Kepler, which they call peas in a pod, is that the radii of neighboring planets tend to be similar. Kind of makes sense, maybe. If they're formed under similar conditions, maybe the radii are also similar. What we find is that this radius uniformity, so here shown basically plotting the inner radius versus the outer radius between planet pairs, that this radius uniformity is actually stronger in overdensities. So despite the fact that we've been reshuffling the planetary system, the planetary radii of neighbors are still the same. So that means planets don't only know about their neighbors, they know about the system that they reside in. There is a degree of uniformity that is system-wide. Again, it's very interesting because it means that planet formation is really a global process. And then here, finally, there is another result from Kepler. There's a dearth of planets at about 1.8 Earth radii. Planets that are bigger are called sub-Neptunes. They're like Neptune, they have a gaseous hydrogen-helium envelope. And planets below that radius are called super-Earths. They don't have a thick atmosphere. They're basically pretty barren, rocky planets. And this is usually explained by the idea that sub-Neptunes lose their gas envelope through a variety of processes. Usually it's thought it might be photoevaporation from the host star. And that then basically exposes the rocky core. So you turn sub-Neptunes into super-Earths. What we find now is here, if you show the planet radius versus the orbital period, here you see the radius value. What we find is that there exists no rocky super-Earths in the field. All of our field planets are sub-Neptunes here. And again, this is still a small number, but it turns out the result is actually statistically significant. And what this suggests is that overdensities play a role in turning sub-Neptunes into super-Earths, somehow helping them to get rid of their envelopes, potentially through perturbation. And you can, if you're interested, you can read more in the paper, we can talk about it later, but we have some ideas about what the physics are that might be causing this. But this is very puzzling. It turns out that actually, it's not just the planetary system architectures, it's actually also the atmospheres that are sensitive to this larger scale stellar clustering. So we've been trying now for, I think, of the order 2 years, but it might be longer. We've been trying to get rid of these results. We've been trying to find all kinds of biases that might explain this. We've been changing the threshold probabilities for distinguishing between field and overdensity systems. We've been making different cuts in stellar age, metallicity, distance. We've been focusing only on specific planet detection methods, even on specific planet surveys, to try and homogenize as much as possible. And we've not been able to get rid of the result. So if any of you have an idea of something that we overlooked, please tell me, because we're still trying to break this. We haven't found it. And so far, the result seems to be that stellar clustering indeed shapes planetary systems. And the reason we still want to break this is that if this is true, it's really an existential point. Because it means that somehow galactic environment matters for the planets that you get out. And that is really fundamental. So we need to understand that. Okay, so the elephant in the room is what is the physical nature of those phase space overdensities? Are they relics of Earth or not? And in this recent paper, just from 2 months ago now, we did this summer, we found that it turns out it's likely not a relic from birth. What we find now is with Gaia, we can look at the global distribution of stars within the Milky Way. So I'm here showing the azimuthal velocity, so the rotational velocity within the galaxy, as a function of galactocentric radius. And what you see is these ridges, these sort of ripples within the galactic disk, where stars are moving in the same way, but at sort of discrete different velocities. These ripples are kiloparsecs long. It turns out that our overdensities here, so overplotting the planetary systems here in blue for overdensities, and in blue for the field and red in overdensities. When you overplot the planets here, it turns out that the overdensities correlate with these ripples. So the overdensities that we find are galactic dynamical features that are several kiloparsecs long. What we also find is that the stellar populations within these overdensities, so now we can start to look at individual overdensities, right? You see here there are different ripples. So we can just isolate, okay, do the planetary demographics differ between different overdensities? It turns out if we look at individual overdensities, we see that they're heterogeneous. So this is showing the stellar age distribution. We see it's very wide. So an overdensity doesn't contain stars with all the same age. No, they're basically anywhere between the minimum and the maximum age that we've been using. We also find that it's not like a simple decomposition into the galactic thin and thick disk, which is an idea that came up at some point in the discussion within the community. No, so they're basically all thin disk stars. So it's not something related to that. And then finally, we find that the planetary system demographics actually differ between the different overdensities. So this is here showing here on the right, basically the hot Jupiter to cold Jupiter ratio. So the very close in Jupiters, how many there are relative to the very far out Jupiters. And what you find here is that in this system, you get a very high hot Jupiter to cold Jupiter ratio, whereas here in the Sirius overdensity, it's a lot lower. And in the field, it's the very lowest, right? As we would expect. So we can now start to link the planet demographics of individual overdensities to what the evolutionary histories of those overdensities might have been. And we hope that that might tell us more about the physics that are driving this. But the conclusion so far is that galaxy evolution is somehow capable of affecting planetary system architectures over long timescales, giga-year timescales, after planet formation. And now with the upcoming facilities, we will actually be able to look into this way more, because we will be able to get statistical samples of thousands of planets, and particularly focusing on the atmospheric properties. So I'm part of both Ariel and the LIFE initiative, where we're hoping to target thousands of exoplanets, characterize their atmospheres, the chemical composition of their atmospheres, and basically start making that link. How does the chemistry of the atmospheric properties actually correlate with galactic environments? And thereby, how does the potential ubiquity of habitable planets correlate with large-scale environments? So this is basically the sort of the 10-year future. Okay. So that brings me to the end here, basically, is stellar clustering drives the Baryon cycle, allows us to trace how galaxies like the Milky Way formed and assembled. It perturbs and destroys protoplanetary disks, and now it turns out it also modifies the properties and architectures of the planet population. And I'd like to bring this back all together by going back to eMosaics, to this movie that I've been showing twice before. right? We see here the cosmological formation of a Milky Way mass galaxy. And in colors, you see the star clusters forming, sort of the clustering that is long-lived. And if we look in e-mosaics at the fraction of star formation here that formed in clusters as a function of redshift, so this is just shown for one of the Milky Way mass galaxies here, what we see is that that fraction of stars that's born in clusters increases with redshift. So at high redshift early in the universe, many planetary systems were affected by the environment. Today, very few are affected by the environment. But you see something else here. You see here, even in the median, you see those spikes. These are galaxy mergers. What happens here is the galaxy mergers compress the interstellar medium, compress the gas. So the gas reaches much higher densities, which means the stars reach much higher densities when they're born, which means that the perturbations of planetary systems are much more prevalent. So what we have here are megaparsec scale events that affect the astronomical unit scale properties of planetary systems. That's how bad the scale coupling is. That's the problem. That's the problem we're trying to solve. And if you look at the solar neighborhood here, this is showing the star formation history in the solar neighborhood. Here is a function of look back time. You see this spike here. This is when the Sagittarius galaxy merger passed through the solar neighborhood, and it caused this upswing of the star formation rate. It turns out this is when the sun formed. So maybe the sun was actually formed in an event like this. And if that is true, then maybe if the solar system really, did not form in relative isolation, then maybe what we're learning from observing protoplanetary disks near the sun today might actually tell us a lot less about our own origins than what we thought. Maybe these are actually very different. We don't really know this yet. So to wrap up, I've been talking about how stellar clustering connects the formation and evolution of galaxies to the formation and evolution of planetary systems. So what I've shown is that stellar clustering drives the Baryon cycle in galaxies. It disrupts giant molecular clouds by early feedback, and we can now use that as a subgrid model in galaxy evolution. I've shown that simulations of the entire star cluster population now allow us to use globular clusters to reconstruct the formation and assembly history of the Milky Way and soon also external galaxies. I've shown that stellar clustering shortens protoplanetary disk lifetimes, especially high gas densities and pressures, through mainly external photoevaporation and very rarely external dynamical interactions. But that's on the short term. On the long term, we find that stellar clustering shapes the planet population, potentially dynamically, right? This is on a much longer timescale, so therefore it might happen. And it does so in terms of the architectures of the planetary systems, but also the properties of the planets themselves. And what that means is that, yes, our existence might be one of the biggest multi-scale astrophysics problems. And it might seem a little bit intimidating to understand this complex ecosystem that you see here. But I hope to have convinced you that this is becoming a tractable problem. We're starting to be able to connect all of those different scales of physical processes. And what that means is that when facing this challenge, we shouldn't look scared, but cool. So thank you very much for listening. And
thank you, Diederik, for such a super nice talk. Is there any question from the audience?
max saturation.
I have a few. I guess I'll start by with a question about the first part of your talk when you show that there were very big differences between the morphology of the star forming regions in galaxies depending on how you set how much momentum you feed back into the ISM. But I was wondering the analysis with star formation itself, right, and in particular with the threshold for a star formation, right? So if you imagine, I mean, I guess that's kind of an unknown, right? I mean, what are the conditions for a star to form in the first place? So if you imagine, you can imagine that if you have a higher threshold for a star formation, you might end up with different clustering properties of the stars, and then the effect of feedback would be different, so and so on. So I was wondering if there is a way of distinguishing the impact of early feedback and the threshold for star formation.
Yes, it's a really good question. So indeed, you're completely right that stellar clustering is not only set by how long you allow star formation to proceed by, say, delaying feedback or letting it start early. It's also set by how quickly star formation can proceed, right? So the actual physics of star formation itself. And I think indeed Melanie showed some examples of that in her talk on Wednesday. So it turns out that's exactly right, which is one of the reasons that we've actually been quite careful here, also playing with the star formation model. I think long-term though, because this is not yet empirically motivated, this is still physical, and we would ideally like to use the same philosophy of actually going to the observations and saying, okay, what does the real universe do? And I think at these resolutions, it's really important to do that because you're not resolving the relevant physics. And you can try and sort of guess what it should be physically, but I'd rather just give up, go to the real universe and put in the right answer. So I think where the answer is going to come from is basically here. So what you see here is that we have this molecular cloud lifetime here with, if we just, so these timelines are made using molecular gas traced in CO and massive stars tracing H alpha. With James Webb, where with the FANCS collaboration, we now have a large program, we will be able to also probe the embedded star formation here that precedes the H alpha. And what we will then be able to do is sort of in a time-resolved way, figure out how quickly those clouds are forming stars as a function of time. So when do the embedded stars show up? When do the unembedded stars start emerging in H alpha? And by using these types of timescales, and therefore also the efficiencies per se, free fall time and so on, as a function of the wide range of environments that we're probing here. So this is only 10 galaxies, but with FANCS we're going to be probing of the order 100. I think then it is actually possible to address that question. Then it's possible to say, okay, we've got this sort of initial star formation phase. How quick is that? What are the key quantities that depends on? And then we can separate that from the feedback that's happening here in the purple range. So I think if we do that, then we get somewhere. But that is still, I would say, 3 years away.
Okay, more questions?
I saw a blip on Zoom.
Could be, you're the host.
Oh yeah, so there is a question by Nate, which I'll read. It says, hi Diederik, thanks for the great talk. My question is, what physical kiloparsec scale processes could affect planet architectures over gigayear timescales that would be able to cancel out the initial densities, which should be orders of magnitude higher, although on shorter timescales? And that is indeed a very good question. So let me go back to the relevant slide potentially. Yeah, I think this is a good one. So, oops, I lost my mouse. There. So indeed, this is a really good question and we don't have the answer yet, but I'm happy to speculate. So clearly, stars are born in more clustered environments than they sit in gigayears later. So why would gigayear timescales be able to affect the planetary systems, but the initial clustering maybe not as much? And indeed, I think the key answer will lie in a couple of things. One is indeed the timescales. So the initial clustering is very short-lived. So that might take maybe 10 megayears or so, typically, for your typical sort of unbound association where stars form. Whereas then here on the longer timescales, you've got gigayears. So that's at least 2 orders of magnitude more time that you have. The problem is, though, that if you look at those longer timescales, the densities are low. And it turns out if you calculate the encounter rate in the field between passing field stars and planetary systems, it turns out that encounter rate is much too low. So if you do that, then you might need to wait for more than a Hubble time before you finally get the encounter that you need to perturb your planetary system. So what we're currently looking at is how successive sort of weak encounters might destabilize the planetary system sufficiently that you get internal chaotic processes that basically redistribute the planets within a system. So we think that that might be a source. But even then, the key problem is basically the angular momentum transport. So you have some, say, distant encounter. How does the angular momentum difference that's imparted by that distant encounter, how does that make its way into the center of the planetary system? Because if that is slow, then the rapid orbital revolutions of the planets can basically adiabatically dampen that perturbation. So what you need is you need an outer planet or so. And it might be that all planetary systems that we know have lost their outer planets. Might be that that has been because of external perturbations. But you kind of need an outer planet to be perturbed, which then goes onto an eccentric orbit, which then perturbs the inner planets. Something like that could happen. It's challenging. And this is something that at the moment we're following this up with in-body simulations of planetary systems to try and figure out exactly what part of parameter space is feasible. But I think this is the sort of the gap we're trying to bridge, is like we've got those empirical constraints. We've not been able to explain these through covariance with any other properties. And then we need to find a way of bridging that to the physics. And this is, I mean, the question Nate is asking here is the big question. It is just based on the demographics of the overdensities that we see here, it's clear that it cannot be from birth. I think a very important argument here is that we see planetary systems being part of overdensities. And for some of the overdensities, we have a rough idea of how long these have been existing. And if you then compare that to the age distributions of the planetary systems, it turns out the overdensities contain planetary systems, both that have formed before the overdensity formed and after the overdensity formed. So clearly the formation of the overdensity is then not a key factor in disrupting the planetary systems, but it's the fact that the planetary systems are part of that overdensity. So yeah, that does seem to mean it happens later, but we're still figuring out exactly how. I hope that answered your question, Nate. And I realize there's a delay on the line, so I'll read your answer soon.
So I do have a question, and it's about the use of the neural networks that you're using. So are you using these neural networks because of the lack of a model to connect the two physical quantities? Or is it because of the lack of, let's say, accuracy or speed of this model?
This is a really good question. And I hope I have a backup slide here, because I have a figure from a paper by Joel Pfeffer that really demonstrates this nicely. And it turns out I don't. So I'm sorry. But basically, this is the key plot. So here. So this is energy versus angular momentum space, where the globular clusters are being deposited. And what you find is that basically, as you go up, you go towards lower binding energies. And there are two ways in which, when a galaxy accretes, it can deposit its globular cluster at lower binding energies. One is by being a really low mass galaxy. If it's a low mass galaxy, then it starts orbiting, it gets tidally disrupted, but it's still very far out in the halo. If it's a more massive, yeah, I started this explanation the wrong direction. Okay. There are two ways in which you can get close in. Let me do it that way. If you're a massive galaxy, then you survive for long as you're spiraling in and you deposit your clusters closing. So that's one, be massive. The other one is accrete early. Because when the Milky Way was lower mass, you didn't have to be as massive to make it all the way in before getting tidally disrupted. So you got a degeneracy there. Basically, if you end up at high binding energies, so down here, like the Kraken globular clusters here, there are two options. One is you were a massive progenitor, the other one is you accreted early. And in the case of Kraken, it was actually both. You can break this degeneracy by looking at the age metallicity information of the globular clusters, because then the age range tells you something about when you might have accreted, and the metallicity tells you something about how massive the progenitor galaxy might have been. But because the assembly histories of those galaxies are all quite different, or quite messy, and none of this follows really neat relations, basically by throwing a neural network at it, you're much better to predict exactly what was going on than by trying to do this, say, analytically or semi-analytically. So that's in this example. In the other example of machine learning that I showed was Sebastian's work. And here, I think it's the only resort, because once you start looking at external galaxies, you want to know, is this cluster in situ or ex situ? And the next step here is going to be to play the same game and say, okay, what is the merger tree of this galaxy that we're looking at? So then it becomes a regression problem again. But basically, if you want to distinguish between these two cases, you're only using things like metallicity, the projected radius, the projected angular momentum, because you have so little information in external galaxies. you see here, if you look at the distribution functions, right, there is overlap between the red and the blue populations in pretty much every slice through the phase space. And again, that means that, yeah, you can probably define some empirical cut through that multidimensional phase space, but that's also what your neural network is doing. So then why not use a neural network and actually do it in a way that's not subjective? So that's the reason that we're doing it this way. And we're actually finding that it works better than if you were to just sort of define a multidimensional plane through this phase space subjectively. So that's why.
Awesome. Thank you. Any last minute question? Otherwise, I think we can stop here. And let's thank Diederik again.